Hello all, today we will be discussing on our third program, that is arithmetic logic unit. So our intention is we have to design a model using a Verilog code which will be doing the arithmetic and logic operations for 32 bits, right? So you already know the arithmetic and logic operations. They are a plus b, a minus b, a complement, multiplication, and or NAND and XOR. So those are the logical operations. Those are the logical operations which we will be performing in a 32-bit. So now you can see the algorithm. First we have to start and initialize our input and output ports. Then we will write a behavioral modeling, and finally we will test by using a truth table. So truth table has to be written, and then we will check the output based on that. So and then we will observe a timing diagram, and finally that will be the end of our program. So let us go with the code. As you can see here, we will be writing the program in Verilog code, right? So the module name is ALU, which is given here. The inputs are A, B, opcode, enable, and Y mul. This is for multiplication and this is for rest of the operations. So because we have to hold the values, so we have here we are differentiating Y and Y mul. So first our input A and B, it is 32-bit. So 32 is to 0, 31 is to 0, that is 32 bits have been taken here. Similarly input B, that is also 32-bit, and input enable is taken. So in order to just make sure that whichever the operation here are we performing, so in order to select that we will be taking this enable. And similarly just to start we will be using this enable, and opcode is to select whichever the operation which has to be performed. And similarly output will be saved here in Y, and the multiplication, since we are doing 32-bit multiplication, so 64 values will be saved. And register, when we are writing a program in behavioral model, we have to consider this register. Our output has a register, so we are declaring it as a register here. And then while writing the behavioral model, we have to always specify this particular code, always at. So we are specifying that, that means we're giving the condition always when, right? So A, B, and opcode. So these are my input here which I have considered. And then begin, we are beginning the code here. So if enable is 1, only then this works. If it is 0, then this particular code will not work. So if my enable is 1, then so case is opcode. That means this is the code opcode which we are using here in order to select different operations. So if it is 0, 0, 0, then it is A plus B. If it is 0, 0, 1, then it is A minus B. 0, 1, 0. So this is 3 tick B, that is 3 bits. We are specifying the 3 bit here. 0, 1, 0, then it is negation, that is not operation. If it is 0, 1, 1, then it is multiplication operator. If it is 1, 0, 0, then it is AND, 1, 0, 1 OR. Similarly NAND, XOR. Finally, even though we can do all the further operations also here, but we will be stick on with this. Finally, since we have started here, we have to default begin and end, and whatever we have started the case, we will end the case. And finally else, in case if this particular enable is equal to 0, then we are going with the BZ. That means we are specifying that whatever the output is there, that will be high impedance state. So finally we need to declare end and end module here. So let us go with our implementation and check with that. So we are using a Xylene ISC, which I have told in the previous videos also. So this is the code, the same code which I have written in the Xylene X ISC simulator. And now first point is you have to check with the implementation and check the syntax. The syntax is proper, you can see it here. And then we can view the synthesizers report, and similarly the RTL schematic. Okay, you can check here the report, the schematic, everything. If whatever you want, you can check it here. And now let us simulate our waveform here. So for that behavioral we have to select, and I have already created a test bench waveform. So I think this is what because you know, right, enable I have given the input as 1. First initially I have taken 0 and then rest all it is 1. Then my input A, which is of 32-bit, similarly B opcode you can see here, and similarly my output. Fine. So this, after this, save it and then simulate the behavioral model. Once you simulate the behavioral model, okay, you can check here. One second. Okay, see, I have given my enable has 1. So if it is 0, right, you can check here. Let me go with output. See, output will be what? Z, irrespective. That is what I've written here, right? So if it is enable equal to 1, then I'll go with this code. If it is not 1, that is if it is 0 or any other value, then we go with the impedance condition that you can see it here. Then I have given certain values here which you have already known, right? So if it is you can see here 100 or 111, 001, then 111, right? And I've given certain values for my A and B. You can check here, I've got my output. So what you have to do is you have to take certain values, write the truth table, and then you need to verify the values for this. That is what you have to do it. Okay, I hope you understand this particular ALU program.